So in this video we're talking about partial fraction decomposition and using it as an integration technique. Partial fraction decomposition is really useful. You don't just use it as an integration technique. Later on in differential equations you use it for inverse Laplace transforms a lot. So this stuff is actually really handy, and you will definitely be using this later on. So basically you start out with an integral like this one, minus x minus 6, and dx. And this integral is, you can't, from the techniques that you should know now, there's no way to evaluate this integral without decomposing it into its partial fractions. So you can't do any use substitution. Nothing will work really. Well, I'm not going to say nothing will work because I didn't go into extensive detail, but the standard method for doing these types of integrals is partial fraction decomposition. So, just as an example of what we're going to get, when you decompose this, you get these two fractions, and if you do the math, this is actually a 2. Oops, a 2. Why am I having such trouble here? 2. Okay. When you do the math and you combine these two fractions, they will give you this fraction. And the logic here is that these two fractions are equivalent to the original one, and therefore their integrals must be equivalent. And these two fractions here are easy to integrate. They're just the ln of the absolute value x minus 3, and then we have minus ln of absolute value x plus 2, and then plus c. So not bad at all once you decompose them. The question is, how do you decompose them? Now, here are the rules, so to say. So basically, if we insert something in here, what you do is you factor the denominator. Let me put this in an integral sign. And if you factor the denominator, you get this. And that should look familiar because these two factors occur in these two. And that's exactly what happens. You factor the denominator, and then you set each factor equal to its own term on the other side. But the question is, what do you put in the numerator? And the first step in this problem would be to write a over x minus 3 plus b over x plus 2. Just any arbitrary number above them. So, and we set that equal to the original fraction, like that. Now, well, there are more rules to what you put up here, and we'll get to that in a second. But now, since these two are equal, now we can multiply both sides by this denominator here. So if we multiply both sides, I'm just going to explicitly show that, just so it's more clear there. So we multiply both sides by that, make a new line. This all cancels to just 3x plus 11. This x minus 3 cancels with that one, and then we just get a. This x plus 2 cancels with that one, and we just get b. Now, there are two ways to do this. The easy way out is to realize that this is an these two sides are an identity, excuse me, and therefore are equal. So any value of x we put in will make the statement is equal on both sides, and then we can use those values of x to solve for a and b. So if we make x is equal to 3, that's going to be, well, 9 plus 11 from the left hand side is 20, and that equals 5a, and then this one vanishes. See, that's the trick, is to use values of x that make a term go away. So that means that a is equal to 4, and that's indeed what we have up here, 4. And then now we use the other one, x equals -2, and when x equals -2 we get -6 plus 11, which is 5, or 11 minus 6, which is 5, and then that equals, well, the a term, the first term goes away, and we have -5b, so that means that b is equal to -1. Then again, that's what we have up here. So let's just yeah, that's fine. Alright, the other way to do this, typically for me, I always try to do this way first, but you'll find that sometimes you can't do this way all the time, because or well, you can always do this way. You can always just pick random values of x, but sometimes you can't make each term disappear and solve for each term, so you have to pick different values of x and then get a system of equations with a and b in them, and sometimes that's not always the easiest thing to do. A way that works with basically the same difficulty every time is to expand this right hand side. This would be ax plus 2a plus bx minus 3b. Oops, b. And now you no, that's good. Now you group the x terms and the constant terms. So this is going to be a plus b x, and then this is going to be our constant. Now, again, we have an identity on both sides. It's equal. So that means all the x terms are equal on both sides, and all the constant terms are. So that means that 3 is equal to a plus b, because the coefficients in front of the x terms must be equal, because this statement is equal. And our another equation is 11 equals 2a minus 3b. So now we have a system of equations. You can solve it however way you like. Basically, it's pretty much algebra at this point. I'll do it, what the hell. So you get a is equal to 3 minus b. Just solve, bring the b over, and then you get 11 equals 6 minus 2b, because we're replacing a, and then multiplying 3 minus b by 2, and then minus 3b, and that's going to be equal to 0. Yeah. Equal to... Oh. That should have been an equal sign, not a minus sign. That's why I went wrong. Okay, so we have 11 equals 6, and then this turns into minus 5b, and then you bring the 6 over and you get 5, and then we once again get b equals negative 1, and then you plug in -1 here and you get a equals 4 again. Either way works. The first way, there's a plane flying by my dorm. I don't know if you can hear it. Anyway, there's always planes flying. or helicopters. But this first method, if you can get away, if you're able to cancel each term independently, then this is the easiest way. If you're not, this way is the second way is the best way. So I use both pretty much evenly all the time. So it's good to know both ways. So that being said, we'll get on to the rules, because I mentioned before about the rules for these numerators. So I'll keep up to here. So remember, these we factor the denominator and then put them in each denominator for their own term. Now, in this case, they were linear. It was just x plus 2. So that's what we're gonna mean. We're gonna say if the denominator is, sorry about that, is ax plus b, then the term you put for the numerator for the right hand side is just a, like we did before. So it's a constant. If the denominator is ax plus b to the nth power, meaning you have the quantity x plus 1 squared or something, you use basically this is what you put as your term. And you know what, I'm just gonna write the term on the right hand side there. That's what you would do. For this, you would do, it would be a1 ax plus b, and then plus a2 ax plus b squared plus and then etc, 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 all the way up to an ax plus b to the n. So basically, like say if you had if you had x plus 1 squared, your terms would be a1, or I use ABC, but you can use a1. It would be a1 over x plus 1 plus a2 over x plus 1 squared. And these are just rules developed to account for every possibility that fractions could be. If in the denominator you have ax squared plus bx plus c, a expanded quadratic that isn't factored, as in this case, then your term would be, you always do a degree lower than the term. But see, I never liked that rule because this always threw me off. Like if you have an expanded quadratic, you use a linear term in the top instead of a constant term. Just like if you have a linear term, you use a constant term. It's one less. So this would be ax plus b over, and then this quadratic. See, you use the constant term. And you know, from there, those integrals are a little bit more tricky. You're dealing with like the arctangents and what have you. And just a reminder, remember this left column is factors in the denominator. Okay, the numerator could be whatever. Now, one final example: if you have an expanded quadratic and it's raised to some power n, then it's the same logic as this. You basically take this expression, except now this is a1 and b1, and then you do the same logic as above, and this is squared and then plus dot dot dot, and then I'll just write it for completeness to the n, or not to the n, a sub n, and then this is to the n. There. So these are your rules that you have to follow when making the proper terms. And one thing that's interesting is if this rule right here, this second rule, if you have let's just copy down these two. X. You have this, okay? If you combine these, then if you combine these fractions, okay, you're gonna get this. Now you can combine the denominators, and then this is A2. Now you distribute this A1 through, and so now A1A is just another constant, we'll just call it C, and then all this is just another constant, we'll just call it D. So really this expression here is essentially the same rule as this one down here. It's a quadratic, and you use a term less than it. You use one less term in the numerator, and that's this term. That's the linear term. And but see, that's the reason why these are split up like this, is because in this expression you have to again break it up into more fractions, and that all boils down to this. So really this second rule is the third rule, but just taken one extra step and broken down again into these expressions. So interesting little thing, a bit of information. Okay, so now we have laid down the groundwork, and I will do, let's check the notes here. I will do another example. Okay. Now I don't have the work in my example, but I have the solution. So hopefully we'll get it. So to me, this is my first time doing this problem too, so we're gonna work through it together. And I feel like it's more realistic if I do it that way, rather than do it perfectly every time. Alright, so let's see. So we got, it's the integral, let's write this down, x squared plus 4 of 3x cubed plus 4x squared minus 4x dx. Okay. Now, what is that? Well, what do we do here? Remember, we want to factor the denominator. So I leave the factoring up to you. That should be, somewhat of an exercise to test your factoring skills. When you factor it, you end up getting this. And maybe take a moment to pause and do that and get this factor, because that's indeed correct. Alright, so now we have our three factors, and they're each linear factors. So we use this first rule up here and break up. See, I'm just going to break away from the integral right now, just do an aside. So there's going to be a over x plus b over x plus 2 plus c over 3x minus 2. Okay, so now we multiply both sides by the denominator, x squared plus 4, and then we have a times x plus 2 times 3x minus 2, and then let's see, that's b x 3x minus 2, and then cx x plus 2. Alright. This is a case where we can use the easier method and eliminate factors, but you could just as easily, well, I can't say just as easily because then one wouldn't be the easier method, but you could easily just expand everything and just relate the terms to the left and the right like we did that first example. So what we're going to do is we're going to just say x equals 0. So that becomes 4 equals, well, let's say you plug in 0, and that's 2 times negative 2, so that's negative 4a, and then these two go out. So that means that a is equal to negative 1. Okay. Next one. When x is equal to negative 2, because the goal here is to cancel out terms. So and you notice that there's, in this particular case and in a lot of cases, there'll be a common factor between two of the terms. And the first one, there's a common factor of x, and then this next one, there's a common factor of x plus 2, and two of them. So if you choose the 0 of that factor, you eliminate 2 terms, and you could solve for 1. That's the logic here. So now if we make x is equal to negative 2, this first term goes away, this third term goes away, and we have negative, let's see, well, negative 2b, and then we have 3 times the negative 2, which is negative 6, and then negative 6 minus 2, which is negative 8. So, and then that equals, let's see, negative 2 squared is 4, 4 plus 4 is 8, then that means that the negatives cancel, and the 8's cancel, so that means that b is equal to 1/2. Okay, the last one is, there's a common factor of 3x minus 2 in two of the terms, and not in this one. So we take the 0 of 3x minus 2, which is x is equal to 2/3. 2/3. Now, plug in 2/3. Don't even have to do work because, well, we don't have to do work for two of the terms because these two are 0, because that's the 0 of 3x minus 2. So now we have c times 2/3 and then we have 2/3 plus 2, and then 2/3 squared is 4/9. 4/9 plus 4. Okay, so let's add fractions here. Let's see, 4 times 9 is 36 over 9, so that's 40 over 9. And then this is going to be, well, 6 over 3, but then 6 plus 2 is 8 over 3. But then 8 times 2, 2/3 times 8/3 is 16/9. 16/9. Well, the 9's cancel. We have 16 and 40. Let's see, factor out. Divide a 4, divide a 2, and then we have c is equal to 5/2. Alright, so we have a, b, and c. So now we can take this, our partial fraction decomposition, and put it back in the integral and replace. Well, a was negative 1, b was 1/2, and c was 5/2. Let's see if that's what I have in my notes. Yes, it is. Okay. So, now these are all just natural log functions. These are easy. Well, these should be fairly easy. So this is natural log of x plus 1/2 natural log of x plus 2, and then plus 5/6 natural log of, oops, forgot the natural log in the second one. There we go. Of 3x minus 2. I got the, it's 5/6 instead of 5/2 because you do a u substitution on this 3x minus 2, and you get du is equal to 3. Or dx is equal to 3 du. And then you divide and what have you. So it's just the chain rule. Then plus c, and that's our answer right there. So, fairly complex looking integral, but when you break it up into pieces, each piece isn't bad at all. Okay, so that's that one. 2 more examples left. The next one is, let's see here. Okay. Let's erase all this. I'll keep the rules up there just in case I need to refer back to them. So we have x over x squared plus 4, and then we have x plus 1. Okay, so this one I made up, and I got an answer to it, and I'm hoping it's right. But the important thing is the method. So I'm fairly certain it's correct. So if it's not, somebody will tell me. But this one, okay. So same deal. We first break it up into its partial fractions. But the question is, what do we put as well, we put each factor is in the denominator, in each denominator. X plus 1, and this one on the right is a constant. But what's this one on the left? Well, it's an expanded quadratic. Okay, this isn't a factored quadratic. It's expanded, so it would actually be this case right here. It would not be this case. It would be this case. That means we use a linear term in the numerator. So that means this is going to be ax plus b, and then this one will be c. Okay, so now we multiply both sides, and we get x equal, multiply both sides by this denominator, and we get x equals ax plus b, and then x plus 1 plus c x squared plus 4. Now, it's hard. You can't eliminate a term that has. You can't eliminate this term at all. There's no zeros to this term. We can use You can use whatever method you want here. You can use a combination of the two methods first we did. But what I'm going to do is I'm just going to expand this. So this is going to be x equals ax squared plus ax plus bx plus b plus cx squared plus 4c. Now we group all the like terms. We got a cx squared over here, so this is going to be a plus c and then x squared. Then we have ax and bx, a plus b, quantity x, and then this is our constant term. Now, there's no x squared terms on the left hand side, but there is terms on the right hand side, so that means a plus c is equal to 0. And that, by the same logic, a plus b is equal to 1, and b plus 4c is equal to 0. Because there's no constant terms, but there is a first degree term, and the first degree terms have to be equal. So, from this, a is equal to negative c, and from this, b is equal to negative 4c. And now we plug these two into the middle, and we get negative c minus 4c equals 1, or negative 5c equals 1, or c equals negative 1/5. But c is negative 1/5. That means a is equal to 1/5, and that means b is equal to 4/5. There we go. Makes sense, right? Not too bad. No Avast. Okay. By the way, Avast, great virus scan. It's free, and it's like the best one I've ever had. It's awesome. Anyway, we have A, B, and C now, and we're going to plug that back into our partial fraction decomposition. Back into the integral dx. And let's see, our A was 1/5, our B was 4/5, and our C was negative 1/5. Well, now we have to do the integral. Well, this term is not beta, that's the natural log. But there's a little bit more manipulating we could do, and I know this looks really ugly. So let's do some little bit more manipulation here. We're gonna do this is going to be we're gonna split it up. So this will be 1/5 and then x over x squared plus 4, and then this one will be 4/5 and then 1 over x squared plus 4. So this first one, you make the substitution of u is equal to x squared plus 4, so du is equal to 2x dx. And you make the substitution, and you're going to get 1/10, because you're going to get the integral of 1 over u du. And what's 1 over u? That's natural log of u. So natural log of the absolute value of x squared plus 4, and that is the first one. The second one, this one right here, you can either do it explicitly. You would use trigonometric substitution. I have a video on trigonometric substitution. You do that substitution, you carry out the integral, and you find out that it's equal to the arc tangent. Or, second option, you look at an integral table, or look in the back or the front cover of your book if you have a book, and just realize that this form is the arc tangent form. But if all else fails, if you can't remember, you can use a trigonometric substitution and you'll get it. So this happens to be well, it's going to be, well, this is your a squared, and it's equal to 1 over a times the arc tangent of x over a. So 4/5 divided by a is 2, so this becomes 2/5, and this is arc tangent of x over a, which is x over 2. And then, of course, this last one is just 1/5 natural log of x plus 1, and then plus c, and there we go. So you notice how they can get a little bit more tricky. Well, that's your answer. Okay, not too bad, not too bad. Last one. Let's flip my notes over. Okay, there's one important rule about partial fraction decomposition that you should know, and that is that the degree in the numerator has to be lower than the degree in the denominator. It has to be proper. So in this case it's improper because the degrees are the same. In order to make the degree lower in the numerator, you have to do long division. And you know, whenever I say this to people, they're always just like, "What? I don't remember that." Well, you gotta you use it. It comes up. It pops its head up a few times. So here I have the long division work. You basically take this bottom one and put it on the outside, and then you say, alright, well, you take the first term, x squared. How many times can x squared go into x squared? That's 1. You just divide them, and you get 1. Then you take this 1 and you multiply it by x squared and put the result here. Then you take the 1 and multiply it by -1, put the result here. Then you subtract this whole line from x squared. So x squared minus x squared is 0. 0 minus -1 is equal to 1. So this is our This is the remainder, and this is part of the quotient. So you write, this is equal to, let me just rewrite this here. You write, well, part of the quotient was 1, and then plus, and you always put the remainder over the term you divided by. So x squared minus 1 in this case. Now, after doing that, after making sure that the fraction is indeed proper, you do your partial fractions. Well, we can immediately do this integral right here, but let's do partial fractions first. 1 over x squared minus 1 is equal to 1 over x plus 1, x minus 1, there we go, which is equal to a over x plus 1 plus b over x minus 1, because they're linear terms. Now again, you multiply by this bottom denominator on both sides. You can forget about this part, and you get 1 equals a x minus 1 plus b x plus 1. And we can take the easy way out. We can say x is equal to 1, and this is 1 equals 2b. So that means b is equal to 1/2, and then we can say x equals negative 1. And that's going to be 1 equals negative 2a, because this term goes out because it's negative 1. And that means a is equal to negative 1/2. So now we plug in a and b into this, and we get negative 1/2, which turns out to be negative 1/2 natural log absolute value. Again, well, that absolute value is very important because you can't have a negative argument. And you put the absolute value because the quantity x plus 1 is allowed to go negative. So you can't just put x plus 1 into the natural log because it could be negative. So you always have to put the absolute value. Oops, forgot the ln again. There we go. And then plus c, but we forgot about this 1 right here. We only did this. So the integral of 1 is just x. And there you have it. So that's pretty much partial fractions in a nutshell. You can, as with anything in math and anything I'm going to put in these videos, you always learn better with practice. So you just do a bunch of problems. They're all pretty much the same, except for when it comes down to doing the integration at the end. Sometimes they can get a little tricky with the arctangents and stuff. But other than that, that's it. Thanks for watching. Like, comment, subscribe, and what have you. Thanks.